Hello, this is Chuck Ridgway, Automation Technology Manager here at Horner. I'm so glad you decided to join us today for another one of our Tuesday live streams. Now, today's topic is one that's really involved with just about every application, certainly all applications that utilize analog sensors. So today's topic is all about analog I/O scaling. So joining me today, Mr. Casey Gardner. How are we doing today, Casey?
Hey, not too bad. How's it going, Chuck?
It's going great. Now, I think we all understand that the whole idea of analog I/O scaling is to take information generated by analog sensors and translate that information into data in our application program that we can use to do control or monitoring. Now, in all your time of helping out new customers or new application engineers or just those that are new to Horner, what do you think is the key to getting that right?
Well, for myself, I think I usually start with the sensor side and see what kind of sensor I'm working with and what type of data it's going to be kind of outputting. So something like a temperature sensor, like an RTD or thermocouple, and then kind of next going into the controller side of what it's coming in as, whether it's again raw temperature data that may be on a certain scale factor, or if there's whether I need to do some math with it to get it to the right value one, or even do some math to get it to another data type entirely.
Yeah, so what you're talking about really is, I think, 2/3 of the whole puzzle, if you will. What's going on with the sensor? What kind of signal is it putting out? How is the data in the controller taking that signal and digitizing it into an integer value? And then the last piece of the puzzle, which is good for folks to understand, and to understand kind of the tips and the tricks, is the programming side to take that integer value in the controller and do the simple conversion to the engineering unit. So using the right instructions to make that job easy. I mean, I think we can all do y equals mx plus b if we have to, but we've got instructions to make that a lot easier, so why go to that trouble? Okay, sounds good. So today, while I'm covering the material, Casey is going to be manning the chat, so as you have questions, feel free to chat those in. He will either answer those right away or he'll save them until the end. And then if you're watching this on replay, like a lot of you do, don't hesitate to ask questions. You just ask it through the comments section, and then we'll make sure we get that question answered in a timely fashion. Okay, let's go ahead and get started. Okay, so here is our program for today. Again, what is analog scaling is where we're going to start, and then we're really going to spend a lot of time talking about how analog data is scaled in the Horner automation product. So what we're mostly talking about here, of course, are the Horner OCS all-in-one controllers. Now, as all-in-one controllers, all of our products have the ability to be purchased with I/O built right in. So you very well may be connecting your analog signals right into the back of an OCS through one of its analog inputs. And all of our OCS products have analog inputs. But you could also be connecting those analog signals through one of our remote or expansion I/O blocks, so we'll cover those as well. Now, in addition to, how is the signal going to be scaled once it gets into the I/O module, we also are going to review scaling logic. How are we going to go about taking that digitized value and converting it to engineering units, whether that's pounds per square inch or bars or degrees Celsius, whatever the case may be, and whether do we want to do that in an integer form or do we want to do it in a floating point form? How would we prefer to do that? And we could do it either way in most cases. And then we're also going to give you a couple hints. So if you're using analog inputs as the process variable for a PID instruction, for a PID control type application, if you happen to have a signal that might be very narrow in its range, we'll give you a hint on how to maybe scale that particular signal so that the PID construction can have an easier time in providing you with effective control. So those are really the topics of our information today. And then, of course, we're going to spend some time with demonstrations at the end. Okay, so let's start with what is analog I/O? Well, I think most people understand, maybe new folks are just getting used to the fact that analog I/O are sensors and actuators whose real-world operation is more than just on or off. In other words, they're providing values, data values, typically integers, that are used in either the monitoring of a process or the control of a process, okay? So an example, for instance, of a digital input might be a temperature or a thermal overload switch. Now that's just going to be on or off based on a thermal overload condition. However, a thermocouple sensor, which is a type of analog sensor, it won't just give you on or off, it'll give you the value of the temperature, for instance. Another example on the output side, because remember, analog isn't all about inputs, there's also analog outputs. An example of a digital output might be a solenoid valve, which is just on or off, okay? But the analog corollary to a valve might be a proportional valve, all right? An analog proportional valve, where you're not just controlling on or off, but let's say 60% off or 70% off, that sort of thing, okay? Now, to make analog I/O integrate properly with your control, you need to perform analog scaling. So that's really the conversion of analog to digital data and digital to analog data to and from sensors and actuators and engineering units. So that's really what the program's all about today. Now, from my perspective, there's really three keys to successful analog scaling. First, understand how the sensor converts its measurement to an output signal. What are the engineering units that it's measuring? Are we talking about pressure? Are we talking about temperature, etc.? And then what's the output signal look like? Is it 4 to 20 milliamps? Is it 0 to 10 volts? What does it look like? And then also, the second key to success is understanding how the analog I/O module digitizes that signal from the sensor into a numeric value. Now that analog I/O module, again, could be a separate module like a smart block I/O I've shown there on the screen, or it could be one of the analog I/O points that's built right into the back of an OCS. Now the third key to success is understanding how to configure and program the controller to interpret that numeric value that was converted from the signal into an measurement or into a measurement in engineering units. So again, the three keys are understand the sensor, understand how that signal from the sensor is converted to a integer value in the I/O module, and then understanding how to program and configure the controller to interpret that signal and convert it to engineering units. So those are really the three keys to success. And we're going to spend quite a bit of time really on, I think, the last two, all right? Because those are the ways that might be different with a Horner product than what you might be used to with another control product. So we're going to spend a lot of time on the conversion of the signal on the I/O side, and then also on the programming to get you the engineering units that you're looking for, properly scaled, of course. Okay, so of course, analog inputs are typically going to be from sensors, and most sensors are going to convert a real-world measurement into a linear electrical signal. Okay, 4 to 20 milliamps is the most common, but you'll also see 0 to 20 milliamps, 0 to 10 volts, 0 to 5 volts, and several others, okay? Now, what the OCS analog inputs will do, and again, whether this is a separate I/O module or built into the back of an OCS, what that circuitry does is it converts that signal, let's say 4 to 20 milliamps, for instance, into a numeric value, and that numeric value is reported in an AI register. The AI registers are the type of analog input registers which accept analog input values. And then the last step, of course, in the user's application program, you need to write some logic to convert that analog input numeric value into the engineering units you're looking for, PSI, bars, millimeters, inches, etc. Okay, so that's really what we're talking about, of course. Now, temperatures are a little bit different. The reason they're a little bit different is because sometimes the circuitry that converts the sensor into temperature is built right into the I/O. Now, RTD and thermocouple temperature sensors, again, because they're so common, there's two ways you can handle those, okay? First of all, you can connect that sensor to a separate transmitter, which is a separate piece of hardware, which converts that signal from the temperature sensor into a 4 to 20 milliamp signal, for instance, and then that 4 to 20 milliamp signal then gets sent to the OCS as a regular analog signal. So that's one way to handle it. And then the other way that you can handle it is by utilizing one of the specialized analog input circuits in, say, the Model 5 or the Model 6 OCS, or one of our thermocouple or RTD input modules, where they actually have the circuitry to interface directly with the sensor and convert to temperature. But the temperature that's converted, or the value that's converted, might need some simple math to get it into degrees Fahrenheit or degrees Celsius to make it an integer, to make it a floating point value, whatever you're looking for in your application. So again, temperature sensors can be a little bit different. Now on the analog output side, because remember, we're not only talking about inputs, analog outputs just work in the opposite way. Okay, it starts from the user's application program, where the program determines how the analog actuator needs to operate. For instance, I may want to decide to close the valve 60%. That may be what I want to do in this machine step for machine control. And then the application program needs to take that desired action, say close the valve 60%, and then scale that to a numeric value, which then the OCS analog output will convert into a signal that will cause the actuator to actually move the valve to 60%. So it's really just the opposite process, but it's very much the same. All right, now I'm going to show several slides here with a lot of detail on them, and I'm not going to spend a ton of time on these slides. I know a lot of people use these videos kind of to reference to after the fact. So when you're in that scenario, of course, you can always scrub right up to the slide you're interested in, pause it there, and soak it in if you want. But really what we're talking about here is, what does the scaling look like from the analog signal that's generated by the sensor into the analog input value, or the integer value that is present in the %AI register, okay? So most general purpose sensors out there are going to be putting out either 4 to 20 milliamps or 0 to 10 volts. And then on the OCS conversion of 4 to 20 milliamps, for instance, 32,000 counts, or an integer value of 32,000, is going to be full scale. So that's going to be 20 milliamps. 0 is going to be minimum scale, or 4 milliamps. Now, if it happens to be that your sensor is a little bit under range, in other words, it's putting out a signal below 4 milliamps, but above 0, you'll see that in the form of a negative value. Okay, and if your sensor happens to be a little bit over range, it's also possible you'll see a value a little bit bigger than 32,000. And with voltage, it's very much the same. Full scale of 10 volts is 32,000. Minimum of 0 volts is 0 counts. Okay, and you may get a little bit of over range as well. So that's the basics of how, in most cases, analog data is scaled on the input side with the OCS and the OCS-IO. Now let's talk a little bit about resolution, because I know some people get confused. They'll say, now wait a minute, this XLE product I have here has 12-bit resolution, while the Model 5, I think, has like 15 or 16-bit resolution. How can the scaling be the same? That doesn't make any sense. Well, in reality, it is the same, because the only thing that the resolution of the reading affects is how many numbers increment or decrement as the signal changes. For example, if you're using an analog input from Horner that has 16-bit resolution, the minimum change is 1 count. So as that signal is very slowly incrementing, you can potentially watch that analog value in the AI register incrementing all the way up 1 at a time. However, if you're dealing with a Horner product with 12-bit resolution, it's still going to be creeping up from 0 to 32,000, but it's going to be creeping up 8 counts at a time, because the minimum resolution from a counts standpoint is 8 counts. Okay, so your scaling is always 0 to 32,000. It's just that the steps that you take between 0 and 32,000 will change based on your resolution. And I will make one caveat here that we'll point out again in the program, and that is that SmartRail actually is the only Horner product we have that isn't scaled 0 to 32,000. It's scaled 0 to 4,000. So that is an outlier there. Okay, here's a chart. Again, I'm not going to spend a lot of time on this, but it basically shows you the scaling and the resolution of some popular Horner automation products, from the Micro OCS, which is our most cost-effective product line in that first column there, followed by a couple of our most popular XL Series I/O options, the Model 3 and the Model 6, followed again by the SmartRail and the SmartBlock. And the SmartBlock is really our premium analog product. So if you have an application which requires really the highest resolution and the highest isolation and those sorts of things from an analog perspective, the SmartBlock is really our premium product. Now, that being said, we have excellent analog throughout our range, and your requirements may very well be met even by the Micro OCS product, for instance. Okay, now let's take a look at an example. Okay, let's say we have a pressure sensor that's connected into one of our OCS products. All right, and let's say the pressure sensor is monitoring pressure in a range of 0 to 10 bars. with a resolution of 0.01 bars. Okay, sometimes with a sensor, an analog sensor, you'll get a resolution specification, other times you won't. Okay, it just depends on the sensor. And then the output of that sensor, again, the input is in pressure or bars, the output is 4 to 20 milliamps. Now, from a OCS conversion standpoint, as we've already covered, 32,000 counts is going to be 20 milliamps or 10 bars. 4 milliamps is going to be 0 counts or 0 bars. And then you can see a linearization equation there on the screen. Okay, how would we convert from counts to bars? Although I'll show you an easier way to do it when we get to the programming side of things. And then if we go through the math with a sample reading of 13,520, we do the math and we see that the end result is 4.23 bars. Okay, so that's an example of getting from a pressure sensor into a pressure reading inside your application program. The second example is the same case, but this time with SmartRail. So really the only difference is that instead of 32,000 counts being full scale, it's going to be 4,000 counts being full scale. All right. Everything else is the same. Of course, our linearization equation is slightly different because our full scale is different. But the end result, if we have the same pressure reading on the pressure sensor, the end result is the same. Okay, so if we have 4.23 bars being read by the analog sensor, we're going to end up with 4.23 bars in the application program. Okay, so again, regardless of the scaling value or the max value, you're going to end up in the same place from an engineering unit standpoint. All right, now let's take a look at a ultrasonic level sensor. Okay, a little different scenario. Now we're not looking at pressure, we're looking at an ultrasonic level sensor, which it has a range of 1 to 25 feet. So pretty long distances, relatively speaking, for ultrasonics. Okay, 32,000 counts is going to correlate to high range, which is 25 feet. 0 counts is going to correlate to low range, which is 1 foot. Our equation is similar but slightly different, as you can see there. If we have a sample reading of 7228 in our AI register, where do we end up? Well, we end up at 6.42 feet. And if we're interested in inches instead, we can be looking at 77.1. So again, these are just different examples of scaling that's done on sensors with different ranges into OCSs and OCS-IO modules. Okay, now let's look at one the other direction. Now we're talking about a proportional valve, okay, where the input to the valve is the signal. Okay, so the input to the valve is the signal, 4 to 20 milliamps in this case. The output of the valve is the position of the valve from 0 to 100% closed, for instance. Okay, so let's say that with this particular valve, and it could vary by valve, the 0 counts is 0% open and 32,000 counts is 100% open. And it could be the opposite. You know, it could be 0% closed and 100% closed. It all depends on the valve. You'd want to check your documentation for your valve to be sure. But in this scenario I've outlined here, we've got a pretty straightforward linearization equation. And if we want to move the valve to 48% open, we can do the quick math and we can see that we need to set our AQ register. Remember, AIs are where analog inputs come in. AQs are where analog outputs go out. So our AQ register would need to have a value of 15,360. And in my example here, if we want that valve to be 48% open. Okay, we're going to talk about temperature sensors now because they're a little bit different. And this is an area I do see customers get tripped up a little bit because we're doing the actual temperature conversion in the OCS most of the time. And when we are, the units that we provide, even though they're already, I guess, converted to temperature, they may not be in the exact units that customers are looking for, you know, whole degrees or 10th degrees Fahrenheit or Celsius. Now, remember, there's still two approaches we can take. If you want to, and you've got an OCS that only has 4 to 20 milliamp or 0 to 10 volt inputs, for instance, you could use that external temperature transmitter that's going to do the temperature translation for you and output that linear signal. But if you want to connect those sensors directly into one of the Horner OCS's temperature type inputs, thermocoupler or RTD, we also actually do more than that. We also do thermistor as well on some products. But if you wanted to do that, then you're going to need to make that connection, configure Cscape for that particular sensor, and then do some really simple math probably to convert over to the units you're looking for. That's really what's involved there. So again, I'm not going to go through this entire chart. This shows some of the differences between some of the different temperature sensing capabilities that we have with different Horner I/O modules. Notice the micro OCS on the left there. For the X4, X7, and X10 versions or models in the micro OCS line, those do support RTD, but only a limited range of -50 to +200C. So they don't support the full range. If your application is beyond that range, you'll need to use an external temperature transmitter and then use the 4 to 20 milliamp of that transmitter into one of the 4 to 20 milliamp inputs on the micro OCS. But if you're okay with that temperature range, which a lot of customers are, in food applications or HVAC type applications, then feel free to use the RTD directly. Okay, so you can see some differences there in terms of the resolution, how the temperature is scaled, what the accuracies are, how frequently the channels are updated, all those sorts of things. I'm not going to go through those in great detail, but I want to show you there is a great variation there. All the way over to the right, if you take a look where the A to D converter used on the Smart Block is quite high in resolution, even though at the end of the day, you're still looking at 10th degree C or 10th degree F in terms of your actual readings. Okay, that last chart was all about RTDs. This chart is about thermocouples. All right, thermocouples are just slightly different variations of temperature sensors. They work completely differently, but they are often used in industry, just like RTDs are, and they're not supported directly in the micro OCS line. So if you're using a thermocouple with a micro OCS application, you will need to use an external temperature transmitter to convert over to 4 to 20 milliamps and linearize externally. But again, lots of variation in terms of the specifications for thermocouples and the Horner OCS product line, and the I/O that's accepted as well. Now let's do a quick example of an RTD input connected directly to, let's say, the XL Series Model 6 I/O. All right, that's one of our most popular XL Series I/O options because it has 6 analog inputs and 4 analog outputs, and each of the 6 analog inputs can be configured for thermocouple RTD, 4 to 20 milliamps, 0 to 10 volt, and even more. So really flexible on the input side of things there. Okay, so let's say we have a PT100 sensor, platinum 100 ohm sensor, connected into a Model 6 or maybe into the Smart Rail. One AI count, in the case of the temperature readings, are going to correlate to either a tenth of a degree Celsius or a tenth of a degree Fahrenheit, depending on how it's configured in the OCS. Or in Seascape, because in Seascape, you can configure for these products, for Model 6 and for Smart Rail, you can configure whether you want your result to be in degrees Celsius or degrees Fahrenheit. And they're going to be reported in 10th degree increments. Okay, so if you select degrees Celsius, then effectively, and let's say you have a value of 100, that means 10.0 degrees Celsius. And if you want to take that exact value and convert it to degrees Fahrenheit, you'll need to do the equation or the math in your OCS, which can easily be done. So there you can see the conversion equations. Now, similarly, let's talk about a thermocouple connected to the XL Series OCS Model 5. The Model 5 I/O has 2 configurable analog inputs and 2 configurable analog outputs. And on the input side, those again are configurable between RTD, thermocouple, 4 to 20 milliamps, 0 to 10 volts, etc. So in this case, let's say we've got a thermocouple type K sensor, and we're going to configure it for 1/20th of a degree C Celsius in the Seascape configuration process. With the Model 5, you don't have the choice between degrees Celsius or degrees Fahrenheit. It's going to come in 20th degree C increments. That's how the value is going to be coming in. It's already going to be scaled to temperature, but it's scaled to degree C, and it's scaled to 20th degree C increments. So if you want to convert that to degree C, what you need to do is you need to divide the value by 20, all right? And then you can cross-convert it over to degrees F through the standard equation that you see there, all right? So let's say we have a sample reading in our AI register in this example of 2030. What does that mean? Well, we divide that by 20. It means we're at 101.5 degrees C. When we do the standard F to C conversion in math in the OCS, we end up with 214.7 F. So again, more examples of how to do the scaling, this time with temperature. This is an important one because this is one that does trip folks up, especially since micro OCS users often tend to be kind of newer users. Of course, there's plenty of experienced application engineers using the micro OCS, but because of its price and its capability, there's also plenty of newer folks out there as well. And the way that the RTDs are scaled with the micro OCS is fixed at 20th degree C increments. Okay, so it's very similar to the Model 5. And remember, its range is limited to minus 50C to plus 200C, which correlates to digital readings between, that's incorrect there. It correlates to between minus 1,000 and plus 4,000 counts. Okay, so that's the scaling. Minus 50C to plus 200C correlates to minus 1,000 to plus 4,000 counts. You've got a simple math equation to get you to degree C. You have a simple cross conversion to get you to degrees F. And there you can see an example with a reading of 3,800. It means that you're nearly at full scale. You're at 190C or 374F. Okay, so another example of scaling temperature in the OCS. Okay, so we've covered in pretty good amount of detail how you're going to take analog sensor data that's being output, let's say, as 4 to 20 milliamp signal, or a thermocouple signal that's directly connected to an OCS and being converted. How do we want to do that in terms of what's the conversion look like? Next, we're going to talk about the programming required to make that happen and to make that happen really easy. Okay, because the final step in those 3 keys to success are doing the programming in the OCS in Cscape to get your engineering units that you're looking for. And by far, the easiest way to do this is using the scale function. And quite a few people, I guess, miss the scale function. I think a lot of people, once they see it, are thrilled that it's there and they use the heck out of it. But some people miss it, and we don't want you to be missing that instruction. So there's 2 ways you can use the scale function to scale analog inputs in your logic. First of all, you can use the scale function in integer mode. Okay, if you're using an integer mode, it's going to round off the result. However, you can very often use some tricks, and I'll show you those tricks, to add some implied decimal points, which can work really well, so that you can stay in the integer form for your data. In many, many cases, you can stay in the integer form, and your end result still has plenty of resolution and gives you great results. So for example, let's say we have a sensor with a 4 to 20 milliamp output, which is measuring pressure between 10 and 100 pounds per square inch. So 0 is 10 pounds, 32,000 is 100 pounds. We could scale it between 10 and 100 on the integer block, but if we did that, we would round off, or it would round off, and we'd have a resolution of only down to 1 psi. And we can do a lot better than that. If we scale instead of 10 to 100, we scale between 1,000 and 10,000. Now there's a couple extra zeros there, and we're actually getting resolution all the way down to 100th of a psi, even though there's no decimal point anywhere to be found. Okay, so that's a trick that you can use. If you just want to stay within the digital form and not mess with floating point, that's something you can do. Now, for many of you, you'd prefer to do it in floating point or real mode. So with this same example, the difference would be here. The difference would be that first, you would need to take the analog input value in your AI register, and you need to convert that integer into a real value into another variable. And then that variable that's been converted to real would go into the scale function. And then your end result is a floating point value between 10 and 100, where you aren't rounding off all the fractional parts behind the decimal point. Okay, so that's the other approach you can take. It does require an extra step to convert your analog input from integer to real. Okay, so each step is equally valid, or each approach is equally valid. All right, let's not forget about scaling analog outputs in logic either, though. And this process is just the opposite. Okay, so we start with the real value for our output command. You know, we want to move that valve 62.5% or whatever the case may be. Then, so we want to scale between, let's say, 0 and 100% on the valve position to 0 to 32,000. That's going to end up in the analog output register eventually. But we do our scale function in the real form. And then when we're done with our result, we take that real value result and we convert it to an integer and then send it out to our AQ register so that the OCS IO point will convert it to the analog signal, which allows the valve to move to the position we desire. Okay, so analog outputs utilize the same function, just the inputs and outputs, if you think of it that way, are kind of reversed. Now, here's a tip. one thing that can happen occasionally with the PID instruction, again, PID is an instruction that's available in the Horner OCS. It's available, of course, in PLCs and many other powerful control products. That basically is a special algorithm or mathematical algorithm that allows you to control a process value quite accurately in a lot of cases. Okay. Now, one thing you have that's involved in a PID instruction is it requires what's called a process value. That's going to be what it's measuring to detect if the process is being controlled appropriately. So if you're doing temperature control and you're going to try and keep an oven at 405 degrees, you're going to need a temperature reading so you can see, well, is the temperature where I want it to be, or do I need to adjust the oven controls to heat up or cool down the oven to get where I want to get to? So the process variable is what we're talking about here, okay? Now, sometimes you can end up in a case where a process variable has a very small range, okay? So a full range would be 0 to 32,000 counts, right? A full integer range, pretty close to full, would be 0 to 32,000 counts. But maybe you have a process where that process variable is not changing very much. So if that's the case, what you really want to do is you want to scale that process variable up to cover much more of the 0 to 32,000 range before you bring it into the PID instruction. Now, why would you want to do that? Well, without going into all the details, effectively what you're doing is you're providing the instruction with more bandwidth for its calculation so it can have more digits of, I guess, resolution in order to make its calculation. So that's kind of a simplified explanation. But effectively, you'll get better results if the input range of your process variable is not too narrow. On this next slide here, we're showing an example where, let's say we have the process variable is coming from or originating from a pressure sensor from 0 to 10 bar. But in this application, we're only going to see somewhere between 4 and 6 bars. Okay, we're never going to see outside of that range. All right, so that would be a range of 12,800 to 19,200 counts. You know, if you do the math. All right, well, that's a relatively narrow range. Not bad, but relatively narrow. So what you could do is use a scale block to scale up 12,800 to 19,200 on the input side to 0 to 32,000 on the output side, and then you could run that value into your PID instruction, and now that value has a much larger range, which gives your PID instruction more bandwidth. Okay? All right. So that's enough of that material. Let's start taking a look at how we would do this in an OCS controller. All right, so I'm going to go ahead and start. Let's do a quick look at our OCS in the overhead view here. So I've got my trusty XL7, and I've got my trusty I/O simulator connected. And what we're doing here is we're simulating two different analog input sensors, both of which have a 4 to 20 milliamp output. The first sensor is an ultrasonic sensor that is measuring from 1 to 25 feet. So minimum is 1 foot, maximum is 25 feet. The other is a pressure sensor, which is providing not just pressure in, positive direction, in the positive direction, but it's giving pressure between minus 100 and plus 100 pounds per square inch. Okay, so at this stage, I'm just showing kind of the raw counts for these particular signals coming into the OCS. That's what I'm showing. So let's go ahead and do some logic to turn these raw counts into the actual engineering units. And to do that, we're going to go to Cscape. And for the most part, I'm starting from scratch here. Of course, I did kind of get the basics of that one screen set up there. So I'm going to go ahead and create a new rung. All right, so I'll drop an always on contact here. All right, and then I'll right click on the power bar and say new rung. And for this ultrasonic sensor, let's just go ahead and stay in the digital form, or I'm sorry, the integer form. Let's not convert to floating point. Let's just do it all in integer. And I'll show you where that can actually work out pretty well. Okay, so let's do this first one in integer. So in that scenario, I can jump right into my scale block. And remember, the scale block is the one we want to use if at all possible. It's located under the advanced math here. So scale, I can select that, and I'll go ahead and drop it on my screen here. Okay, so what's the input of my scale block? Well, the input of my scale block is going to be the signal, or the converted signal, coming from the sensor that's coming into analog input number 1 or %AI1. And I have created down here, I've created an ultrasonic, that's the name of my variable. It's called ultrasonic, is an integer-based variable, and it is mapped to %A1. And I'm in variable-based advanced ladder here, so I have the ability, using the program variable table, to map where I need to certain variables. And in this case, I want to map this variable called ultrasonic directly to %AI1. And then while we're here, I'll show you the fact that I've also directly mapped another variable called pressure into AI2. That's going to be my -100 to +100 pressure sensor that we'll get to in a minute. But let's go ahead and start by scaling, staying in digital form, and staying in integer form, I should say, not floating point form, staying in integer form. Let's start with scaling this ultrasonic sensor. Okay, so our input is going to be the variable called ultrasonic. Okay. All right, and that is mapped directly to %AI1. The minimum range coming into that value, at 4 milliamps, we're going to be looking at 0. At 20 milliamps, we're going to be looking at 32,000. Now, what's my output going to be? Well, I need to create a new output variable that is scaled to my engineering units. And my engineering units are going to be in feet. So anywhere between 1 and 25 feet. All right, so let's go ahead and create a variable called tank level. All right, and let's go ahead and identify the fact it's an integer. And if I were to execute this right here, that would absolutely work. Oh, I've made a mistake already. I always forget this step. The first thing you really need to do when you do a scaling element is select the format that you're looking for. So in this case, I want to stick to integer form, so I need to select integer here. So ultrasonic is an integer variable. Tank level _ integer, which I'm just creating now, that's also going to be an integer value as well. So since I'm creating this anew, I need to press the right arrow key here and the check mark. It gives me the opportunity to create this on the fly. I do want it to be an integer, and under the global variables is fine, so I can just say yes here and OK. Now, if I were to say OK here, what would happen? Well, as my value for my sensor came in from 0 to 32,000, I would be doing the conversion to feet, but I'd be chopping off everything after the decimal point. So I would literally have only a resolution of 1 foot. That's not what I want. What I want is much better resolution than that. So what I can do, as long as I keep the values below 32,000, because anytime you're doing an integer calculation, you want to keep all the values involved in the calculation at somewhere at 32,767 or smaller. Okay, but in this case, if I just add a couple zeros on my input side and my output side, now I'm going to be scaling 0 to 32,000 coming in to 100 to 2,500. So effectively, now I have a resolution of 1/100th of a foot. Okay, that's not bad. I can live with that for sure. So I'll say OK here. I'm going to go back to my, for the first time showing you guys, I'm going to go ahead and go into my user interface here. And let me just go ahead and I copied this data object. I'm going to go ahead and modify this. Now I still need this in the decimal form, okay? But now my variable is different. All right, now I'm interested in tank level int. That's the variable I created. And then when I display this, it's no longer in counts, okay, but it's in feet. And I can show on the screen, I can show a decimal point, even though technically it's just an integer value. All right. Okay, I think that's the way I want it. So now when I display this, I should be seeing not just counts, but I should also be seeing right here the ultrasonic reading in all the way down to 1/100th of a foot. All right, so that's how I did scaling in this case without even leaving the integer form. Okay, now let's work on our pressure translation, but this time let's go ahead and do it in floating point. We could do it in integer as well, but let's do it in floating point for illustration purposes. Okay, so I'm going to create another rung. Okay, so again, At Horner, you can't directly connect a function block to the power rail, so you always have to have at least one contact, and that makes the always-on contact very popular. Okay, now before I can do my scaling block here for floating point, I need to take that analog input coming in, that variable coming in that's currently an integer, and I need to convert that to a real value, because anytime you do real math, and an integer and a scale block is a math block, you have to have all the operands that are in the same form. So I need to use actually a conversion operation from integer to real. I'll drop that on the screen. Okay, the input, or the integer is the input for my conversion here, is my pressure sensor that's mapped to %AI2. I had already created that. Now here is where I need to create a new real variable, and let's call this pressure real. All right. I'll hit the button here because I need to create this on the fly. I haven't actually created it yet. Okay, I need to make sure that it's in the real format. Everything else here is fine. I can say yes and okay. And so now I've taken the pressure reading coming in from my analog input. I've converted it to another variable that happens to be real. Now I can go ahead and grab my scale block. And this time, again, make sure that it's the right form, and I do want real this time. So the input of this block is going to be my pressure real variable that I just created. Okay. Now, it's coming in again, 0 to 32,000 counts, and it's going to go out -100 to +100. However, I still need to create a new variable that is the scaled version, and this time let's call it the vessel pressure real. All right. Okay. Oh, I forgot to finish the process of creating it, but Seascape reminded me, so no big deal. It's real, what I'm looking for. Say yes. All right, so that's the only logic that's required here as well. Let's go back to our screen. All right, and let's finish this up as well. I'll copy this, paste it. Just makes it easier, so I don't have to create it from scratch every time. Let's get it more or less lined up. All right. Let's go ahead and switch first to a 32-bit value. Next, let's switch to floating point format. And then finally, let's select our variable, which is vessel pressure real. Okay. Again, we're not in counts. This time we are in PSI. And our legend, it could still say pressure, but I'm going to go ahead and change it to say vessel. Why not? Okay, okay, and okay. Oops, I didn't get my data display right. Okay, this is -100 to +100, so I need to get that data display proper. So let's say we want to display 3 on the left and 2 on the right. So let's go ahead and pick that one. All right. Now I believe we're ready to download. So hopefully I didn't make any mistakes here. And we can go ahead and download. So Seascape's figuring out what changes I've made. It's getting those changes ready for download, and then it will start the download process. All right, let's go back to our OCS. All right, and we can watch the program finish downloading. All right, just another few seconds here, and we should be in good shape. All right, there we are. So as you can see, let's start with the ultrasonic sensor. All right, I'm at 360 counts. So we're looking at the left side. So we're almost to 0. We're not quite to 0, but we're almost to 0. All right, and as I increase that value, you can see as our counts go from 0 on up, our distance is incrementing right along with it, to the point that if I continue all the way up to maximum here, we're going to see a maximum of 25 feet at 32,000 counts. Okay, and then similarly with my pressure, and again, I'm looking at a low pressure, and that's scaled -100 to +100. So we're near 0, but not quite there. As I increment up, we get what we want. Okay, finally going into a positive pressure as we're approximately mid-range. And then if we go again all the way up to the top, we can see that we're at full range and at the value we're looking for. Okay, so you can see we use two different approaches here. With the first approach, the ultrasonic, we never left integer form, and we got good resolution, so no issues there. With the pressure sensor, we decided to do it in floating point form, so we had to do a conversion first. But the end result was the same, effectively. So there's two ways to solve that problem, and we just showed you both, and that they can in many cases both be equally as effective. Okay, so I'm going to go ahead and bring in Mr. Casey Gardner. Okay, so Casey, any questions that came in during that presentation?
I'm not seeing any. Oh, I got one. Let me double check here. Coming in from Peter, is there another service pack going to be released where all the tag names are automatically sorted alphabetically in the drop-down menus? So service pack related.
Sure. So, okay, so if you're talking about, and we love questions, they don't have to be directly related to the actual topic. So in this case, what he's talking about is the program variable table. So let me go to Cscape, and I'm going to show you that. So he's talking about this and the fact that by default, the variables are in the order in which you enter them. So I entered these variables first, I entered these variables last. So they're not in alphabetical order, they are in the order in which you added them. So we do plan to have a configuration option where you can choose the default order for your variables, whether you want them to be by default in alphabetical order or in the order in which they're created. Today, it's just the order in which they're created. Now, that being said, if you press this name column here, it will go ahead and alphabetize them for you. Okay, so you can get them into alphabetical order, but you have to actually press this button here on the header. Okay, so, but yes, Peter, we do plan on making a configuration option so you can choose your preference for the order in which the variables are displayed in the variable table. Okay, so hopefully that answered that question. I'll bring Casey back in here. Okay.
Sure, it looks like he was specifically referring to when you're selecting a variable inside of a function. So I think when you hit the drop down after you're actually selecting one inside the function block.
He was talking about,
so that's a good
yeah. So he was talking about the variable browser, right? Yeah, and
yes.
Same thing. Yes, absolutely. That's part of the process, or part of the. We have a feature request that's been submitted and approved that will give you the ability to select, do you want those alphabetical order or in the order in which they were created? But it's not in there yet. So yeah, very good. Anything else?
All right. I think that's it.
All right, very good. So hopefully you'll find that analog scaling, especially when you take advantage of the scaling block, is pretty straightforward. Just remember the 3 keys to success. Study your sensor, understand how it scales the signal that it's sending out for an analog input, for instance. Understand how the OCS or controller is going to be converting that value into an integer value, and then use the scaling block to scale it into engineering units. Okay, thanks, Casey. All right, so let's not forget, every Tuesday at 2 o'clock, we have another live stream where we cover a technical topic, some quite simple, some quite advanced. And if we take a look, for instance, at our September schedule, what we've covered so far and what's yet to go, we have yet to cover compare functions. So compare functions seem straightforward, but don't forget we have time and date compare functions, which a lot of folks forget about, and we're going to highlight those next week as well. So if you have some scheduling functions that you'd like to perform on your machine, the compare functions that utilize time and date can be very handy for that. Also, there's the details on the compare function. Again, always Tuesday at 2 o'clock. And don't forget, you can always watch our videos on demand on our YouTube channel or on our website when you have a particular need to look up a particular topic. Okay, well, let's not forget to subscribe and ring that bell so that when we put out new content, you'll get a notification of that. And we, again, appreciate the fact that our subscribers have really grown over the past several months. And don't hesitate to join us again next week or anytime, Tuesday at 2 o'clock, as we cover another technical topic. Everybody stay safe out there, and we'll see some of you next week.